Hi and welcome to the lesson about idempotency in stateful streaming processing. So here I will show you, I would say, three different scenarios you may probably consider while you define your ID generation. And typically we'll do this with an Apache Spark structured streaming job. So our stateful logic just takes this grouped data and sorry, that's not this one, and accumulates some values like mean event time and mean append time. From these two inputs, we are going to generate an output structure with three different three different types of IDs: random, event time, and append time. So what's the difference? The difference between them comes from the data we are taking to generate the ID. First, when it comes to the mean event time, so as the name indicates, we get the first event time in the logs. It can work most of the cases, but if you have some late data coming in and you reprocess your stateful pipeline, well, the ID you generate may not necessarily be the same as the ID generated in the previous run when you didn't have this late data. When it comes to the append time is the time we are retrieving, I would show you that just here from Apache Kafka topic, from Apache Kafka record, I would say, because remember, record is composed of key value that typically I think you will consume the most often, but you can also get headers or timestamp, which are two kind of metadata associated with each event. So here we get a timestamp that we consider as an append time, so the time Apache Kafka added the given record to the topic, to the partition. And here you will see the difference between these two approaches. When it comes to integrating late data, you will see that in one case the ID is idempotent, it's always the same, and in another it's different. So let me start everything, Docker Compose involved, and later the demo topic. So I have a topic, PD idempotency, and this time too I will use a console producer because it's easier to demonstrate. It's easier to use in this demo, in fact. So I adding the first record for the letter number C. Now I will start the job. Only when the state expires I will return something to the application. So here we have the state which is still alive. I will add a new record, this time for a different letter. Okay, nothing happens. So I'm going to add another one. And here we should generate the output for the stored letters. And as you can see, we have these IDs. So let me copy them. Just to have something aside when I will restart the consumer. And now I will stop this job. So just to show you, I have the checkpoint location defined for the job. I will not change it. And now I will add a new record, a record that will be a late record for the state A. As you can see, there is 5 seconds of the difference between them. And now when I remove all the files from the checkpoint, so I remove the files just to define the reprocessing moment. So I want to I'm saying here that I want to remove 2 last micro batches, right? So batch number 4 and batch number 3. And now I will restart the job. So typically I should generate the output again, but you will see that there will be one difference in the output. Well, 2 differences. So the state is reloaded, and now I have my closed state. And what is the difference? No, well, of course, the random ID will be different each time, so typically it's not the best idea if you want to implement an idempotent generation on top of stateful streaming data. When it comes to the event ID, you can see that for the record number B, when we don't have any late data integrated after the restart, well, the ID remains the same. So typically, if you don't have this risk, well, you can try, or this risk represents really few use cases. You can try this strategy and see what it gives in your data, but you can see that it's a bit risky because for the event A, we integrated late data, and obviously the ID is not the same between the runs. When it comes to the append time is consistent, so even if we get late data, we can always generate the same ID, simply because the order of adding this data to the append only log to the partition in Apache Kafka doesn't change. In this demo, you saw three different idempotency generation strategies. So random is a strategy to avoid at all cost. Of course, if you don't care about idempotency, well, it's quite easy to use, but otherwise you should either prefer the event time or the append time based. If you want the strongest guarantee, you should always rely on the append time because it never changes, even if you integrate late data. Otherwise, if you want to have something maybe more meaningful from the user perspective, and instead of generating a hash, as I'm doing here, generate the event timestamp, well, maybe this event time is not that bad, but keep in mind that in case of late data and reprocessing, well, you can break the idempotency. Thanks for watching, and see you in the next lesson.